So then moving on, so we can take a look at some other important functional groups, such as carbonyl function group. For the carbonyl function group, we are going to have the following arrangement of the atoms. So it's a carbon double bonded, specifically double bonded, right, to bonds that make a double bond. So it's a carbon double bonded to oxygen, and then this carbon can be also having or it will need to have two single bonds to be a proper tetravalent carbon, right? So if we look at this arrangement of the atoms and the bonds around them, then we will see the so-called carbonyl functional group, right? So that is going to be a very common functional group in various organic compounds, right? So then where can we encounter carbonyl functional groups? So it could be encountered in other functional group such as aldehydes and ketones, for example, right? So for aldehydes, we are going to have the following composition of atoms. It's going to be COH, right? And then we can have some attachment to maybe something like that here, right? So maybe it's going to be carbon with here like, 3 H's, right? So, but if we look at this arrangement, specific arrangement of the atoms, we are going to have the aldehyde functional group. So for the ketones, we're gonna have a little bit different arrangement of the atoms, which is going to be also containing the carbonyl function group, right? So that's your carbonyl functional group right here. So then it could be attached to maybe some sort of CH3 piece, and that's a single bond right here. But now we are going to have, instead of H, we're going to have the carbon here, right? Which in turn is attached, for example, just an example, for is attached to 3 hydrogens, right? So for the ketones, we are going to have this circled combination of atoms, which is going to be looking like that, right? So that's a ketone functional group in the circle. So let's move on to more functional groups, such as, for example, carboxylic acids. So as you can see, the theme here is that we are going to have a specific arrangement of atoms, right? So to make a functional group, a peculiar functional group, right? So for the carboxylic acids, we're going to have the carbonyl functional group, right? Attached to OH, right? So that's going to be an example of the carboxylic acid functional group. Of course, it cannot like float in the air, right? So carbons are tetravalent. So this right here will be a carboxylic acid functional group, which can be attached to something else, such as maybe carbon, right? Another carbon with 3 hydrogens on it, right? So these are 3 H's. So that's going to be a specific compound that contains carboxylic acid functional group as one potential functional groups in it, right? So COOH, as we might call it. So that's a carboxylic acid functional group. So then let's take a look at some more examples, right? So we have also esters, which are known as derivatives of of carboxylic acids, because you can synthesize via specific chemical reactions esters from carboxylic acids, right? So esters will be looking something like this. So we'll have CO, then oxygen here, and then we're going to have not hydrogen attached to this oxygen, but we're going to have specifically carbon attached to maybe, for example, 3 other hydrogens, right? So it is just an example. So that's one of the keywords that you need to pay attention to here, right? So then we must have one more valence here, right? And then maybe we'll have another example, right? We'll have carbon with maybe 3 more hydrogens here. So, but then what we are going to look at is this combination of atoms, right? So CO, OC, right? So this circled combination of atoms will make the ester functional group. So again, pay attention to how the atoms are arranged and how they are bonded, right? So atoms and bonds. So sometimes you will see very similar functional groups that have kind of like Similar number of carbons and oxygens, but there is like going to be somewhere a single bond instead of the double bond, and all of a sudden it's not an ester group anymore, right? So please be careful here. So kind of like pay attention to details. That's going to be kind of the skill that we are going to like keep in mind here. So finally, amides. Let's take a look at amides. Amides will be looking something like this, right? So it's going to be, again, so the requirement for an amide functional group to exist will be the presence of the carbonyl functional group tied to NH2 functional group. That's an example of an amide, right? So maybe we're going to have one more carbon with three H's right here. And now all of a sudden we have a specific amide, right? So we have your functional group amide present in these organic compounds, right? So amide functional group must have the following combination of atoms. So that's going to be CO and H2, right? So that's going to be your amide functional group. So if you look for something like this, right? So you have carbonyl tied with a single bond to NH2, you are going to have an amide in your chemical organic chemical compound, right? So now let's move on further. So we are going to take a look at some more details related to alkanes now, right? So we kind of like ventured from alkanes to various substituted organic compounds where we not only have the carbons and H's, right? That's what we have in alkanes, for example, or hydrocarbons, broadly speaking. But we also were looking at some other atoms. Other atoms can be present in organic compounds, so it doesn't mean that we are not going to have an organic compounds anymore. If we have oxygens or even sulfur atoms, we might as well have some other atoms, other substituents, as we call them, in organic compounds, right? So that can be achieved through various chemical reactions. In a lot of cases, starting with alkanes, for example, we can synthesize some more complex organic compounds that would contain, for example, oxygens, chlorines, sulfur, nitrogen, and so on. There's going to be a particular number of atoms that we are going to have instead of just or in addition to just carbons and hydrogens. So that's going to be true about like organic chemistry compounds in general. Not only we're going to have the carbons and H's, but we're also going to have some other atoms in organic compounds. Let's now take a look at some more in-depth features of alkanes. So alkanes are hydrocarbons, so they can only contain carbons and hydrogens. What's also true about alkane molecules is that carbons in those molecules have only 4 single bonds, right? So then what's also true about alkanes is that there is potentially several million molecules of that kind, right? So as we can imagine, we can have different number of carbons in the alkane chain. Maybe we'll have only one carbon, right? Maybe we'll have 10 carbons connected to one another. So, and they can be connected also in different ways, right? For example, if you can imagine, let's say 10 carbons, right? So they can be connected in a straight chain of just 10 carbons. In other cases, it's going to be something more complicated, and it's known as branching, right? So we can have the carbon chain that consist, for example, of 6 carbons, and then also there are going to be maybe like 2 carbons attached to the third carbon in this chain, right? So in any case, there could be like a variety of various structures which are peculiar to alkane molecules. Let's now try to draw those alkane structures in various ways. For example, so let's just start with something simple, such as 5-chain carbon, right? So and then 5-chain hydrocarbon alkane, right? So here there's a 5-carbon chain. 5-carbon chain. It's going to be looking like this, right? So it's just a straight chain of 5 carbons. So now if you want to make it alkane, right, we know that it is a hydrocarbon. It only contains single bonds surrounding each carbon. So it's going to be looking something like that, right? So now I'm going to add 2 more bonds here. And now I'm going to populate those free valences with hydrogens only, right? So nothing more. No nitrogens, no oxygens, nothing like that, right? So because I'm going to have like a pure alkane hydrocarbon, right? So in that case, I'm going to add H's like that, right? So these are my hydrogens attached to the carbons. So in this case, I have just drawn the so-called expanded formula, right? So for just a straight chain of 5 carbons in my alkane. What else can I do? So I can also draw other kinds of formulas, right? In order to maybe accelerate my writing of those formulas, right? So for instance, there exists the condensed formula, right? I can use this as an example and then show the condensed formula for this particular compound, right? So in this case, see what is going to happen is that instead of like drawing out every bond in this CH3, H3 because there are four hydrogens, right? So in this CH3 piece, I'm going to just go ahead and say, well, carbon is attached to 3 H's, and it's going to be like that, CH3, okay? I have 1 carbon and 3 H's in this CH3 piece. So now, by the same token, if you look at this CH2 piece, you are going to do something different, right? So you are going to call this CH2. So CH2, okay? So CH2 is going to be right here. So what we're going to not lose is that we're going to not lose those bonds between the carbons, right? So we'll show the bond here. And then we will show another bond here. So these bonds are related to the carbon-carbon bonding, right? So because we understand that the carbons need to be connected to one another, so with this single bond. So now if you look at this situation, right? So you're going to show another bond to the following carbon here, and then it's going to be just still a single bond leading to the carbon. Okay, so in this case, we will understand that this bond is not between H and this carbon, right? Because H is single, is a like monovalent atom, right? And then those 2 H's are attached with just 1 bond each to this carbon here, right? So consequently, these H's cannot be attached to that carbon, for example. So then we're going to, okay, well, look at this CH2 piece and then show it as CH2, right? So don't forget 2. Then we're going to CH2 again, and then we're going to CH3 to cap things off, right? So this is going to be our so-called condensed formula, right? So next one that we are going to have is going to be the carbon skeleton formula, which is going to be a little bit different representation, even like more condensed representation of hydrocarbons, for example, right? So what do we do here, right? So in this case, we are going to have to look at the lines and angles, right? So basically, if I want to show the example of the carbon skeleton formula using this molecule, I'm going to be drawing something like that, right? I'll start with a dot that will represent the carbon, right? And then I'm going to show this bond, right? So that's, let's say, carbon number 1, right? 2, 3, 4, 5, right? Let's just number them. And then we're going to go this way. 1, it's going to be carbon, right, represented by a dot. So then I'm going to show the bond to the second carbon. Then I'm going to go down. That's going to be third carbon, fourth, and fifth, right? So now I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I have 5 carbons now, right? So I'm just trying to show those kind of like the places where carbons are at. I'm going to show them with the thick dots just for the better representation of this molecule, right? So then what I'm not going to show is that I'm not going to show the hydrogens because the hydrogens are going to be implied as well as the carbons, honestly, will be implied. So what you're going to do here is that for the condensed formula, not for the condensed, for carbon skeleton formula, you are going to show the bonds only between the various carbons, right? And then everything else will be implied. For example, what's going to be implied? Implied will be also the carbons, right? So carbons will be positioned either at the ends or at the angles, right? So we have here the like vertex or the angle, here another vertex, right? So three vertices, three carbons, right? So then we have here an end and we have another end, right? So that's going to be two more carbons. So total we have five carbons, just like in this structure, right? So those structures are basically equivalent. They're just drawn in different fashions. So then, since we know that the hydrogens are not shown, they are implied, we can figure out how many hydrogens are attached to each carbon, right? So let's say if this carbon has two explicit bonds, then it can only possess two more hydrogens, right? So whatever is not shown, it's either carbons or hydrogens, right? So in the vertex here, there is a carbon, right? So we just kind of like unravel that and we see the carbon there, right? So then we have two more bonds. Okay, great. So they are there. So then two more hydrogens can be attached to this carbon right here. So if you look at this carbon, same situation here will happen with this carbon. Two hydrogens can be attached to this carbon because this carbon already has two valences busy, right? Consequently, if it can only contain hydrogens, then at max there will be two hydrogens, not three, because if you try to attach three hydrogens there, you will make a pentavalent carbon, right? So this carbon here at the end has one bond explicitly shown. Consequently, it can have three more bonds, which are not shown, which are implied, right? So if nothing else is shown, then it can only have the single bonds to like three more single bonds to three more H's, right? So that's why we're going to have this end here as that piece here, right? Carbon with three single H's attached to that with three single bonds. So by the way, double bonds and triple bonds will be shown explicitly as well, and then you'll be able to like figure out how many H's are on those carbons with double and triple bonds. Okay, so then moving on. So moving on, alkanes can also exist as isomers, right? What do I mean by that? Isomers is a very common feature of various compounds in organic chemistry, which means basically that the molecular formulas of the two compounds may be the same, right? So, but the structural arrangement of the building blocks in the molecule is different. Let's take a look at alkanes. Alkanes can exist as isomers. Let's take a look at our compound, some kind of like alkane, which has a straight chain of four carbon atoms, right? So we're going to show the alkane, which looks like this, right? So it's going to be four carbons in a straight chain, right? So that already sets the tone for a particular arrangement of the building blocks of this alkane molecule. Then, of course, we're going to show our hydrogens, which are going to be like that, right? So we also have in an alkane molecule carbons with four single bonds only, no double, no triple bonds, no other atoms, right? Of other elements. So this is going to be just like one possible isomer, right? That pertains to the molecular formula, according to the general formula of alkanes, CnH2n plus 2, right? We have four carbons and we have respectively total of 8 plus 2, 10 H's, right? C4H10, in other words. However, what could happen is that the isomer may exist, right? So let's just say it can exist, right? We'll not be concerned how to make it, right? So there are chemical reactions ultimately for that. So that's an answer to many problems in organic chemistry. So, but let's imagine now that we have something like this. We have now a straight chain of 3 carbons. And let's imagine that there is going to be the carbon branching off like that. So here, I'll show you how we are going to achieve the same molecular formula. Let's just beef it up with hydrogens, right? So we still must have the same molecular formula. So if here we have C4H10 as the molecular formula, so here in this isomer on the bottom of this whiteboard, we are also going to have the same molecular formula of C4H10. C4, so far so good. Now only hydrogens can be added, right? So let's add hydrogens. So here we have a single bond. Okay. So this carbon has to be tetravalent. 1 bond is engaged. So we need to show 3 more bonds and 3 more H's only, right? So that's it. So basically, now you have here, right? So you have C4 and then H, how many H? 10 as well, right? So that's the same molecular formula, but you see the arrangement of the building blocks, which are basically carbon and hydrogen atoms, in a particular fashion connected to one another. So this arrangement is different from the molecule on the top to the molecule on the bottom, right? So you see 4 carbons in a straight chain. Here we have it. 3 carbons in a straight chain, and then 1 carbon is attached to the middle carbon. So basically it's a different arrangement. It is not the same, right? So that's like what we are going to deal with here. As opposed to conformations of alkanes, conformations are peculiar to one and the same compound, right? So what do I mean by that? So let's say we are going, conformations are not isomers, right? So they are just various conformations of the same compound. It's a various, let's say, spatial arrangement of the same compound, right? Various spatial arrangements of the same compound. That's how we can describe conformations. So let's say we're going to have the, just for the sake of the example, carbon skeleton, some kind of alkane consisting of 4 carbons, right? And then it's going to be looking something like that. So we have carbon, 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 and carbon, right? So here we are going to have a straight chain of 4 carbons with the respective number of hydrogens attached to that. So as you can see from the general formula of alkanes, we are going to have C4H10 here. Just like that, right? So we're going to have 4 carbons, and then we will have a total of 10 H's, right? So that's all good. So now, according to the conformation definition, what's going to happen is the rotation about this carbon-carbon single bond. Let's single out this bond, for example, right here. That's your carbon-carbon single bond. So it turns out it's physically possible to perform the rotation about this single bond, right? So if you grab this atom kind of the carbon, this carbon atom mentally, and start the rotation around this bond, around this carbon-carbon bond in this direction, you are going to move this carbon into this position eventually upon the rotation around this bond. And then you're going to have a different conformation, right? So let's just show the arrow here. And then we're going to show the different conformation, right? It's not going to be an isomer of this compound. It's just going to be the conformer of this compound, because we're not breaking the bonds to rearrange the carbon chain, for example, right? To go from the straight chain of 4 carbons to the chain of 3 carbons with another carbon attached to the middle, right? For that, we need to have the breakage of the bonds, right? Here, we're not breaking the bonds. We're just rotating around the carbon-carbon single bond. That's all it is, right? So thereby we're changing the spatial arrangement, but we're not breaking any bonds, right? So that's going to be the difference between the conformers and the isomers, right? To make an isomer, we're going to break the bonds, right? So in this case, we're not breaking the bonds, so we're going to have just a different conformer. So that's what conformations are about. So this kind of doesn't stay, it kind of stays on top of this carbon-carbon bond, right? So like this, CH3, so then CH2, is here. So that's going to be our CH2 here. And now this carbon, imagine that we are going to swivel that, we're going to do the rotation around or like around this bond, and then this will cause this atom to move here. And now this carbon is going to be ending up here. So now you see you have a different conformation. It's kind of like shaped differently, right? Those two compounds. Here it's going to be like this, right? So it looks like a chair, actually. That's what they call it, right? Chair, like this, right? So you go down, up, down, up. Here you go like this, up, down, down, and up. So that's a different conformation. So if you kind of like trace it, right? So if you show the skeletal, actually, or a line angle structure to this compound, right, this conformation is going to be looking like this. So that's your 4 carbons, right, with the respective number of hydrogens attached to them. If you look at this conformation, it's going to be represented as such. So you see, it's a different shape. But ultimately, the arrangement, right, so the connectivity of the building blocks didn't change, right? You only had the rotation around this bond, which moved this carbon from the down position relative kind of like to this spatial arrangement to the top position, right? And now it moves from here, if you mentally think about this, to here, right? So nothing else changed. No bonds were broken. To make isomers, you will have to break the bonds and rearrange the compounds. Here, you still kind of like have some like rearrangement, right? So, but you don't break any bonds. So that's going to be the difference between the conformers and isomers. Isomers will be made by breaking the bonds. The conformers will be made by rotating around the single carbon-carbon bond in case of alkane conformers specifically.